Hello, everyone. Welcome to Calc 2. Today is March 24th, and I wanted to give you a couple reminders that WebAssign's due on Friday, and I want you to continue to upload your notes each day. So today we're going to spend it talking about knowing what test to use. You've now learned every single test you're going to about proving whether a series converges or diverges. And so now you're going to see, how do I tell which test to use? All right, so let's take a look. So the book gives a prescription for some things to run through in your mind when you're looking at a series. So let's say I'm looking at a series, the sum of an. The first thing I always think about is, does the nth term approach 0? Does the nth term approach 0? If not, the series diverges. That's called the divergence test. So that's the first check. If the nth term goes to something not 0, then it diverges. If it goes to 0, then you've got to see whether another test will tell you. The next thing you ask is the series of a special type? So the special types that you've learned are geometric. You've learned the p-series. Let's see, let me move this out of the way a little bit. You've learned telescoping series. One second. And you've learned alternating. These are all special series that follow particular patterns. You'll just have to know what a geometric series looks like, what a p-series looks like, what a telescoping series looks like, and an alternating series is pretty clear. All right, if none of those tests work, you want to ask whether you can use the integral test, the root test, or the ratio test. And last but not least, if those fail, you're going to need to ask whether you can use one of the comparison tests. So let's erase this. One second. Can the series be compared to one of the special types? Okay, that's great. So those are the 4 things you have to do. Sorry, my handwriting kind of gets bigger and smaller. They're having some trouble with the stylus. Anyway, those are the 4 things you want to use. So let's take a look at a couple series and see what we can do and why we do what we do. So let's look at an example. First example, we'll look at this sum right here. Okay, so when you see the sum, something should be triggered in your mind. You see we have 9 to the n over n squared. So I know you guys don't think much yet about what functions get big faster, but one rule of thumb is that exponential functions get big much faster than anything polynomial. Just look at a graph bit and you'll see. And so what that means is, let's see um, what the divergence test tells us. So let's look at this limit as n goes to infinity of the nth term. And we're going to replace these by x's. So we can actually evaluate this limit. Well, what do we see? We see that the numerator is going to infinity and the denominator is also going to infinity. So that means we can use L'Hopital's rule. And we get 2x in the denominator, and we get the natural log of 9 times 9 to the x in the numerator. Well, the denominator is still going to infinity, and the numerator is still going to infinity, so we need to use L'Hopital's rule again. And now we see that the limit is equal to infinity, which is definitely not 0. And so what this tells us is that our series diverges. By the divergence test. Okay, excellent. However, not all series are so easy to show that they diverge or converge. So let's do another example. And this is the sum from n equals 1 to infinity of -1 to the n times 2 to the n over n factorial. All right. So right away, you should be thinking ratio test because we have factorial and we have an exponent. These are classic series these are classic functions that indicate the use of the ratio test. So what that means is if this is our term an, our an plus 1 term is -1 to the n plus 1 times 2 to the n plus 1 over n plus 1 factorial. So we need to take the limit as n goes to infinity of the absolute value of an plus 1 over an. And what we get is kind of a mess. Well, after we take absolute values, we get 2 to the n plus 1 in the numerator here over n plus 1 factorial. And down here we have 2 to the n over n factorial. All right, so let's move this down. And we can rearrange all this. So this is the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. So what we see is we get some cancellation. And what we're left with is a 2 in the numerator and an n plus 1 in the denominator. And this is equal to 0, which in particular is less than 1. And so this tells us that our initial series converges absolutely by the ratio test. All right. So let's do one more. Two more. This one's pretty speedy though. N to the negative 0.5. Well, let's think about that for a second and write it in a slightly different way. This is 1 over n to the 0.5, and we see that is actually a p series with p equal to 1/2, which is less than or equal to 1, which tells us our series diverges by the p-test. All right, so that was an easy one. Let's do one more, and then I'll give you some to do. Now, in all of these cases, I want you to determine whether it converges absolutely, conditionally, or it diverges. So let's write out this expression. Okay, so I see this series, and what's the first thing I notice about it? I notice that it is alternating. Okay, sorry, that's the bad handwriting there. So this is my term. So an for now is n plus 1, 2 over n times n plus 1. And what we notice is that the limit as n goes to infinity of the a sub n's, well, you have a polynomial of degree 1 in the numerator, and you have a polynomial of degree 2 in the denominator. So we know that this limit must be 0. And so what it tells us is that our series converges by the alternating series test. Okay, but we want to know, does it converge absolutely or conditionally? That is the question. So we need to look at the series of the absolute values. So what we need to do is we need to consider the sum of the absolute values, which are n plus 2 over n times n plus 1. Now, does this converge or diverge? That is the question. So we need to figure out how to show that. Well, we see that this is a rational function. So whenever you see a rational function, you always think limit comparison. And we see that the degree of the numerator, the biggest polynomial in the numerator is n, and the biggest term in the denominator is n squared. So we're going to compare this to the series where the bn's are 1 over n, and the an's are this polynomial over here on the left. So we take a limit as n goes to infinity of the an's over the bn's, and we get the limit as n goes to infinity of n plus 2 over n times n plus 1 over 1 over n, which is the limit as n goes to infinity of n plus 2 n, excuse me, n plus 1 times n over 1, and you see that these cancel out. So we get the limit as n goes to infinity. Wow, rough day here. N goes to infinity. Of n plus 2 over n plus 1. We have the same degree polynomial in the numerator and denominator, and so we get a limit of 1 because the leading of the leading terms is 1. That's bigger than 0. And so what it tells us is this tells us that our series must diverge by the limit comparison test. Because the series that we compared it with diverged as well. Okay, so now that's good to know. Let's summarize. So this series that we began with converged, but the series of absolute values diverged. And this tells us that our original series converges conditionally. Converges conditionally. So this series we began with right here must converge conditionally because it converged, but the series of when you took the absolute values, it diverged. All right, so you've gotten to see us use the divergence test, the ratio test, the p-test, the alternating series test, and the limit comparison test all at once. So now it's your turn to work a couple problems and see what you can do with them in your notes. And I want you to just look at them and try to identify what series test to use. Sometimes you have to use more than one. But being able to recognize what test to use is a very good skill. It's basically a pattern recognition skill that we want you to develop in a pretty sophisticated environment, an environment where you don't know everything there is to know. And so you practice it here, which will better prepare you for your classes in the future. All right, so you have these series. I want you to try and determine whether they converge or diverge. It might take a test or two, but you'll find out. So I look forward to seeing what you've done. Take care.